Hello, how are you doing? Good morning. Pierre speaking here on part 8 of Quasar Training. For your information, after part 7, where we've been exploring a few of different interesting ways that you can play with design and classes, I cleaned it up slightly. So I simply removed this old motor type and the relation to temperature probe. So this is the status at which we should enter the new part. So please do the same if you follow this training, which I hope you do. In this part, I'd like to get you familiarized with calculated variables because they will help you to solve a lot of very common problems when making control systems information exchange using OPC-UA, because they simplify things. They shift the control over calculations from the server to the end user, so you are kind of freed from doing a lot of things in your source code. So calculated variables are variables defined in the configuration, and this is the primary takeaway point here. So remember or recall that in the previous parts we've been adding cache variables, and we did that in the design. And whatever we put in the design requires recompilation. So of course you can add another variable in the design, but then you have to recompile, and that possibly changes your configuration schema. So it's not very dynamic thing. While calculated variables you add in the configuration. Configuration is something that's loaded at runtime, does not require any recompilation of the server, so it has a lot of advantages. And of course, you don't have complete freedom of configuration when doing things in configuration. For instance, you cannot, of course, in C++ without recompiling the code to run some C++ code. So this is not the type of calculations we can do, but you can still do a lot of interesting things by defining an analytic expression. So in other words, some sort of mathematical formula. So you create a calculated variable that is expressed as a formula where the inputs are either constants, and that's of course boring, but what's more interesting are variables that are actually coming from things you defined in the design. So when you have your rotational speed, and let's say an example here, this is expressed in RPMs, but imagine your client or your user or somebody like that wants to have it expressed in period. Okay? Now, of course, you can put a cache variable in the server and do the calculation in the server, but why would you do this if there is a very simple mathematical relation between RPMs and period? That would be simply 1 divided by the RPMs, and then you get your period. Okay? And this you can attach at runtime with a lot of freedom, so that's the primary advantage. So let's do some really very basic example. So as we said, in the server we publish motor's rotational speed, and so far it was a complete random number. So just to make it a bit more realistic, I will now change this to publish something less random, because as you remember, so far it was like complete random from almost 0 to whatever maximum integer you can find. So as you remember, the place where we published the motor RPM was of course device logic object, so was this dmotor class. And in the update method, we call set rotational speed, and that used to be random. So what I will do now is, let's say I'll publish 500, which is 500 RPMs, which is rather realistic rotational speed, and I will simulate something like noise, which would be like random modulo, let's say, 20. Okay, so we have something between 500 and 519, which, is quite a decent simulation of what could be the measurement. Okay, so let's give it a go. Okay, and then I run my server. And then let's subscribe to rotational speed, and as expected, I can tell it's like about 500, something between 500, 519. Okay, so makes a lot of sense, much more sense than before. So now, now I'd like to express rotational speed, but in terms of period. So that would be like rotation period. I don't know what's the proper name in physics, but you probably know better than me. But how do I do that? So I'm not touching the design now. So in other words, I'm adding a calculated variable. I'm not touching my design. I'm not touching my source code. I'm going solely into config. Okay. And now look, I switched to let's say graphical editor or design editor in Eclipse XML tools. And if you look at the content model, you can tell that when I add things, I always see this calculated variable. And the meaning of that is you can always add a calculated variable like everywhere. You're free to do that everywhere, wherever that of course makes sense. So since I published my rotational speed per motor, of course that would make the most sense to actually add the rotational period at the level of motor. So that's what I'm about to do. And now look, I add a child calculated variable. Okay, I give it a name, and that would be a rotation period. Or, if you can comment for this YouTube video, like what would be the proper name, just let me know. And then I have to define the formula. And this here I'm adding like the basic version of the calculated variable is where you define what formula, what will be the value of this variable, but there's few more advanced options, like you can also decide what will be the status based on a formula or things like that, which we cover later on. But since this is period, the period is a reciprocity of frequency. So I'll just do 1 by, and what will be the one? How do I get the rotational speed? Well, this will be the address of the variable. So you can always either find this from Eclipse, but now another I'm showing you the UA expert method just to teach you how to take the address of a variable. It will be very, very useful in real life. So if I want to take the address of rotational speed, like address meaning an OPC-UA address of a variable, look, I click on rotational speed, and then in the attributes pane of UA expert, I find this node ID. Okay, there's a namespace index. There's identifier type, which will be string for everything that Quasar does. So it doesn't have to be string like for OPC-UA, but in Quasar we use only strings. And then you find this identifier, and this happens to be controller1 M1 rotational speed, which is not very shocking because it's like navigating hierarchy with going into the child by dots. So it's a convention that it's also you can see in C++ or other common languages. Anyway, here is a famous bug of Eclipse not able to paste nicely. So this is what I'm doing here. So I'm saying 1 divided by control1 blah 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 blah, and I'm only restarting the server. I of course don't have to recompile. Let's see what happened. I refresh that, and now I see rotation period. And what happens is I get this value, and voila. And let's say I want to have this in milliseconds, just to show you that it works. So I'm saving my config. I'm again restarting the server, and now what I see is this is my period in milliseconds. Okay, so that was the basic usage of calculated variables. So let's talk a bit on possible applications. So we can use calculated variables to express things in different units. For instance, we have a server that publishes as volts. We want millivolts and convert bars to pascals and other types of units from the same family. Then we can express things in different quantities, like convert frequency to period. So it's basically one input and one output, which means the function will refer just one input is just a conversion of quantity. Then we can use that for calibration, which means our server delivers some uncalibrated value. And we have to apply calibration to this, which is, I don't know, it's just adding a constant, maybe linear or quadratic, whatever. And especially if constants can be stored in XML, then this is especially attractive. So you can have different calibration constants for different objects and keep that all along in the same configuration file. So you can easily imagine adding a formula which is, imagine you have volts, which is uncalibrated readout, and then you add volts calibrated or something like this, which is basing on volts, but applies some calibration function. Then you can define wholly new quantities. That means that so now we enter the domain where you have actually multiple variables that you want to bind together to make one new quantity. So imagine you have some sort of a device that consumes power, and what you measure is the current drawn and voltage. So you can of course multiply both and publish the power drawn by the device. So you can have a calculated variable which simply multiplies them in the formula. And then you can also use it for checking for validity of data. So if you look carefully, what you can add when you right click and add attributes, you can find status. So normally status is always good, and the formula applies to value calculation. But you can, in addition, add a formula that will evaluate the status. So you can have one formula. So in one calculated variable, you can have one formula which calculates value and another formula which calculates the status. And for instance, if some inputs considered for value calculation are out of range, for instance, then the status will be bad. You can also add a calculated variable that outputs a boolean. So something like good, bad computation for value checks or something like that. And where to find more documentation about calculated variables. Don't hang up yet. I mean, I'm not giving you this reference to say it's the last slide. No, we actually will enter a few more interesting topics, but I'm just showing you where to find this. So when you clone your Quasar repo, and okay, we did that in part 1, I think. Then in calculated variables doc, and you can find this HTML, and that is your reference for calculated variables. And then you have some information like how do they compare to cache variables, and you have a table with all operators and built-in functions and things, and also what you can put for configuration, right? And some examples and counterexamples. Okay, so now I'd like to show you a few bit more advanced examples. So for this, I'd like to get back with my config to, I think, the plain state that I had before. So sorry, this was let's clean up. So I think this was the state which we had when we started part 8 of this training. So you imagine you start using formulas, calculated variables to more advanced problems like just conversion of frequency to a period. So formulas tend to get bigger, and you can have multiple variables that are used and different operators, and so they quickly grow. That's my message. They quickly grow in the text representation, which is not easy to for maintaining. So you can help yourself using a few interesting features. So first of all, in the example that we just did, we used the full address. So you had to paste the full address, but you don't have to do that. You can use some dollar expressions that we have in Quasar. And the first of them, which is very useful, is this object address. Now, what does it do when you write this in your formula? The whole expression from $, until the very end of the string, so $this object address, will be substituted with an OPC-UA address of the object where you define your calculated variable, which means if I have a motor, this is where we had our previous example, and I add calculated variable, and if I write here this object address, this will evaluate to motor. Okay, so I don't have to type this controller1.motor blah blah blah. So this will evaluate to the particular motor. So I can add then my dot as before, and I can write rotational speed. And let's give it a try. And I have, oh, I didn't give, I did not assign it a name, sorry. So rotational speed 2, for instance. And then I rebrowse, and well, I have this one, which basically is a copy of the first one. Okay, but I did not have to use that address, you know. And the advantage is that it's much easier for replication. Okay, it's really much easier for replication, which doesn't mean I'm inviting you to copy paste, but when we apply few remaining features, then you'll see how to profit from this or similar features. So this object address gives you, well, this object is quite logical, as that's the name. So this object address will give you the motor, but sometimes you actually want to refer to an object which is, for instance, your parent or grandparent or whatever, and this you can do as well. And for this we have another dollar expression. So we have parent object address, and to demonstrate this nicely, I would need some variable on the level of controller, and I don't have any. So I thought I will demonstrate this to you with another interesting example, which is now I'll add a calibration constant into my config file as a calculated variable. So that's the whole point, that you can also use a calculated variable to generate a constant, of course. So what I do is add before calculated variable. Why I'm forcing this to be before? Because Quasar instantiates variable in the order of their appearance in the XML file, which means, you know, if I add this after motor, then of course I'll not be able to use it in the motor. So I'm gonna call it, for instance, RPM calibration offset. So my idea, just for your for a bit of background here, I thought that since we have a motor controller which controls multiple motors, and maybe the method which is used to read the current rotational speed is not ideal, like everything in the real world. So the method adds some error, which is just a constant, so it can be calibrated by using a constant. And so this is the constant which I'll use to get a more precise calibrated measurement. So let's say it will be like -100 RPMs, just an example. So then what I do is I have my calculated variable, which is rotational speed. So what I will do now is I will expose a calibrated rotational speed, and the value of that will be the value of what motor publishes plus the offset. But the offset is defined on the level of controller because the offset is the same for all children of the controller. So it doesn't make sense to apply the same offset many times in motors, it should be defined in one place. It's also easier for maintenance. So that's what I'm achieving right now. So what do I do is I'm now taking this from my parent, and so that would be parent object address, and num levels up will be 1 because we reach to the parent, and then the name obviously will be RPM calibration offset. Okay, I'm doing this quite live, so I can make mistakes here. So we'll see. So what happens now if I rebrowse that guy? I see this calibrated rotational speed, which is 100 less than the rotational speed. Okay. The reason why sometimes you see like a shifted value, like like it's slightly delayed, is because in OPC-UA we have sampling, which might hit on the boundary of update. So that's the reason for your information. Anyway, so what we have here simply adds the calibration value. Okay, so this is another takeaway. How do we use something which is on the parent? So that's the operator, and this is how we define a constant. So the next thing is, let's keep moving on. So then it happens, at least in practice, many times that you use the same formula multiple times. So imagine you have something like multiple analog inputs or multiple temperature probes or whatever, and you want basically the nature of the thing is that you will apply the same formula on all of them. Yeah, so you don't want to do run around and do copy paste, and we wish that you be able to apply something better. So there we can use something which is called a generic formula, and here's how it works. So when I have my config file, as you see, you can add something like calculated variable generic formula. So let's try to use it. And this is what happens: calculated variable generic formula. And the name will be, let's say, calibrated rotational speed. And the formula, I will simply take from what I have here. Calculated variable. Okay, so I cut this thing, paste it here. Voila. And then here I use another type of dollar expression, which is apply generic formula. And I say which formula I want to apply, which will be calibrated rotation speed. Right? Let's give it a try. Does it still work? Voila! By the way, now the time is not shifted, so we are not really on the boundary of update, so it strictly follows. So the difference is just 100 as we wanted it to be in the offset. Anyway, so what's the power of this? Is now, look, we have another motor and we want to use the same formula. So what we can do is I just take this, actually I'm not sure how to do that in Eclipse. Maybe I better do this directly via source. So we have another motor here. Okay, so I'm adding the whole definition of this calibrated, the calculated variable. So I'm taking the whole thing and I'm pasting here. Calibrated rotational speed. And it's again the, apply generic formula. So let me try to test it. And then what happens is I will rebrowse here. And now I have that thing but for the second motor, right? So voila. So you can very easily apply the same formula to many things. So there's one important note to make to make here when it comes to apply generic formula. So this dollar expression as of the moment, which is like Quasar 1311, it just pastes the formula which you defined in the in the definition where you had the generic formula definition, right? So there is nothing like argument substitution. So this we plan to add in future, but there is no argument substitution yet. This might be done, but we don't know when. Okay, so some takeaways from this part. First of all, we have calculated variables because life teaches us that they are very often very useful for defining variables at runtime with values defined at runtime, which use different variables to make up their own value. We can use them for changing units, for changing quantities, for calibration, for defining new quantities, and for checking for validity of data. The feature is quite well documented. So if you're looking for particular operator, particular function, you can look into that HTML file of Quasar. And when your config file starts growing, you can use a few interesting methods to keep it well maintained, such that the amount of work is reasonable. So thanks for your attention. That was part 8. See you in part 9.